if my point Q is here, then the segment just below it is S1, and if Q is over here, your answer should be there are no segments below it. Is the question clear to everybody? And as I ask, please open your cameras, because not for me, but I want to break you into groups, and then I think that as a courtesy for other members in your groups, it would be nice to open your camera.
So just to check, the points of the segment are not necessarily on the strip, right?
Q is on the endpoints of the segment. One is to the left of the strip, one is to the right of the strip, and none of them is inside the strip. So there is no thing as a segment that don't cross the strip. I have, let's zoom it out. Here is my strip, and each one of the segment is going all the way from left to right. So as far as the strip knows, it's a full line. It's not just part of it. So this, I'll use red. This is forbidden, that a segment starts inside the strip but goes outside. It cannot start inside the strip. It needs to start to the left of the strip. The segment needs to end to the right of the strip. Okay, and as we said, no to cross each other, and yeah, and the question is, how can I arrange them in a data structure so that once I give you a query point, I'll know immediately who is a segment below me in times log n. It's not a hard question, but you can do it wrongly. Is the question clear to everybody? I mean, if it would be just, if all the segments were horizontal, then of course I just need to store the numbers, the Y value of each one of the segments, and then I'm just doing binary search among these values. So if all the segments will look like S1 and they were all horizontal, then you don't need anything beside storing the Y value. But well, I definitely have segments of some arbitrary orientation. So again, any questions about it?
I have one other question. Are the segments in increasing order, like how you've drawn them?
Yes. Yeah. They are in increasing order. Increasing order inside sigma itself. Inside the strip, sigma.
So I might have missed this, I'm not entirely sure, but are we to assume that none of the lines can cross each other?
The segments don't cross each other inside sigma. They can do whatever they want, including crossing each other, like maybe S3 and S2 continues to the right and do cross each other, but their intersection point will not be inside the strip. And my query point is guaranteed to be inside the strip. Okay, I'll break you into groups and swing between you, and I think that it's an easy question, just little trick to pay attention to. Okay. Very good. Did I collect everybody? I think that everybody's here. Who's willing to risk his neck? Does anybody figured it out all the way?
I'd like to volunteer.
Okay, go ahead.
So for the solution we came up with, like you should for a binary search, you'd start from the centermost line segment on one side of the line segment. Check to see if you need to go higher or lower, and you just essentially perform binary search, and then you'd also do it on the other side to make sure that you're accounting for the leverage of the line segment.
Okay, so I'm asking, for example, if S3 is my median segment, median meaning, let's make it an, let's have a S7, let's have S7 here, so I'll have an odd number. So S4 is a median, right? Or yeah, 1, 2, 3. S4 is a median. If I also have S7, so S4 is a median, and I want to know if Q is above or below S4. Everybody understand why I picked on S4? Because I have 7 segments. I just think about them as a binary search. I want to ask if I'm happen to be on the median itself, possibly, or is a median segment above me or below above Q or below Q. So I pick S4, and you're suggesting, and go ahead. And now you're asking.
You're searching for which side Q is on, and so based
Right.
on that,
so what I'm storing actually in my data structure, it might save some time. I can store either the endpoints of each segment directly, or I can store for every segment, for every segment, the equation y equals alpha 4x plus beta. This is an equation of a line, right? Y equal constant times x plus beta, or you may know it as mx plus n. It will be beta 4. That's the equation of the line that goes through the segment. Equation of the line that goes through the segment, or the containing the segment. As you'll see in a second, it's not necessarily to think about it, but conceptually it makes sense. For a moment, to think about the equation of the line that containing the segment. And now that's for S4, that's why I have alpha 4 and beta 4 over here. And now I'm giving you Q, and all you need to ask is, I'll take the XY coordinates of Q, place them here and here, and ask if I get equation side, or if this Y is larger than alpha X plus beta at the segment, implying I'm above the segment, or if I'm smaller than, then I'm just below the segment. Make sense? So in this way, for S4 itself, I can ask, am I above S4 or below S4? And similarly, I continue my binary search. The example of Q over here, I'm below S4. That's why I'll keep asking only on the lower subpart of the array. Correct. If Q is below S4, then I know that if there is any segment that is just vertically below Q, it should be in the lower part of the array, or it should be on the upper part of the array had Q been above S4. So the idea is that you're just performing binary search, but instead of holding the endpoints, or instead of comparing the xy of q to the xy of a single point, I'm comparing the xy of q to the line that contains the segment. In other words, the moment that I'm referring to this equation of the lines that go through the segment and do it for all the segments, essentially I'm storing implicitly these huge number of different y values for every possible x. One of you suggested, and the intuition was completely correct, let's, for every possible x value between x1 and x2, keeps a sorted array. So I'm just saving this extra effort by saying the array is the same, but the exact y values that I compare to, I want the y value at q itself. I want the y value at q itself. So to know if this value, y value, on the segment itself, I'll zoom out because this image looks horrendous. Here is S4 zoomed in. Here is Q, which coordinate X, Y, and to have Q below this below S4, meaning that at the X coordinate of Q, what is a y coordinate of the line through the segment versus what is a y coordinate of q. Is this exactly the same? Is q below or is q above? So I can store, instead of the segment, to store the lines that go through the segment, because that's all I compare to. And once I got the answer with the middle segment, with a median segment, then I can continue my binary search either on one side or on the other side of the array containing all these segments. Now, to answer the above-below question, I can answer also using our favorite clockwise versus counterclockwise description. If you don't want the equation, then let's just check. If I'm going from the left point of the segment, let's call it P4 because I'm in segment S4. Let's go from P4 to Q is a bad word because we used Q for query. So let's go from P4 to P4 bar. So if I'm going from P4 to P4 bar and then to Q, am I going counterclockwise, which means that Q is below the segment, or am I going, if Q is above the segment, then you would have gone clockwise? I think that as usual I'm making it the other way around. Clockwise if I'm going from P4 to P4 prime to Q, and if Q was above, then you would have gone, switching color, then you would have gone counterclockwise. Right? That's another way to ask above or below. So once again, either you are keeping the exact equation of the segment, the exact equation of the line that go through the segment, and then you're just putting inside the x and y coordinates, and you see if y is smaller, equal, or larger than y when I'm placing on, or you're lazy to store the exact equation, but instead you're implying the formula that check orientation of 3 points, clockwise versus counterclockwise. And that's only to answer whether Q is above or below Q4, and then I'm continuing to the median of either the lower half array or to the median of the upper half array. And it's acute trick, it shows you that we can do this binary search also with geometric objects. Even though the exact y value changes, the order does not change as we are changing x and y. So it's Q-trick by itself, but let's start with the class, and you'll see other applications of it today. Where is my OBS? Okay. And voila. Okay. We want to start with basic technique in computational geometry. We already saw quite a few, but a few more. Let's talk, and for a while we will stay in two-dimensional world, and we'll concentrate on partition of the world into maps. There will be states or regions or countries, and with boundaries between them, and we need to store it. Maybe for GIS, Geographic Information System, maybe for robotics, maybe for graphics. Let's see one way to understand what can happen in the plane and how do we store it as a data structure. So our first topic is a doubly connected edge list data structure. I know that Amir and other might have seen it in graphics. So what happened when I take the plane and I want to partition the plane? I have the whole two-dimensional plane, and I want to partition the plane into, say, states, regions. How does it look like in general? Well, in general, the three basic concepts that I'm going to use are that I have one or more faces. What is a face? Face means that I can move 2 points lies in the same face. If I can move from one point in this face to another point in the face, and I don't need to jump over any boundaries. I don't need to cross any of the boundaries that I created. That's our defining like the face. For example, the regions of the Voronoi diagram that we have mentioned. We might have edges, this region, the edges, and we have the vertices, specific points inside the face. For example, where two edges intersect. Two edges start or end. In graphics applications, maybe all my faces are all triangles, possibly. Then it will be a triangulated partition. Or commonly, you'd like to say, I'll give some information with each vertex. In graphics application, it would be, for example, color, shade, texture, location, or maybe this is a two-dimensional skin, two-dimensional manifold that describes two-dimensional regions, but I'm only defining the skin of a three-dimensional object, whatever. So I have vertices. Usually the vertices contains a lot of information. I have the edges connecting the vertices, describing something about the who is which face bounding which other face. And I have now the faces themselves, other three, well, other third object. And we'll see various relationship between them, like how the number of edges, the number of faces, and the number of vertices all refers to each other. Let's see how to store all of it in a way that enable us to manipulate it geometrically, to run various questions. So I can store for every face who are the vertices in the face. I can say every face needs to know who exactly are the vertices in this face. But vertex takes a lot of information. Start with, I care about it's a long float, presumably you cared for all the digits that you might want to get. You want it very accurately. And I just see a note that my internet is shaky. Let me know if you miss me. Vertex is an expensive thing, and I am concerned about concurrency problem. If I'm changing attribute of a vertex, did I change all the copies? In short, from various reasons, I want to store the information of a vertex only once. I don't like that a vertex might appear on many faces, but it's a bad idea that I'll store each face will know all the information about the vertex. So maybe I'll store the information. I can also ask for every face to know all the edges inside the face, which is kind of okay, but note that one edge might contain many, one face might contain many edges, and one vertex might appear on might border many faces as well. So let's see how DCEL suggests to store it all in elegant, more or less way, and with not too much memory and with minimum redundancy. I definitely don't want to store information more than once, because then I'm always in the risk that I'll modify something, and when I'm modifying it, the process at modifying it there are two copies to be changed, concurrency issues. You might have heard about it in database. I have two copies of the same data. I have a process that changes one of them and doesn't have enough time to change the other, crashes at the middle of the running, and then I have issues of two copies that contradict each other. So I don't like all of it. So doubly connected edge list, in short DCEL, it stores both the geometric information, what are the vertices, what exactly are the edges. It stored topological information like that Arizona and New Mexico shares a boundary between them. It doesn't tell us where is the boundary, but it says they are both neighboring to each other, so it's topological information, like neighbor, which state, which face is neighbor to which one. And attribute information, for example, in graphics, I'll assign to each vertex a color, and color inside the vertex will be some obtained via linear interpolation, for example. So it's similar, it's not exactly identical to the half-edge data structure. So what is the idea about the half-edge? I'll think about a normal edge that connects two vertices, and I'll break it into two twin half-edges. One that goes in this direction, another one that goes in the opposite direction. Sounds strange. We'll see in a second how it looks. Okay. So instead of one edge, I'll keep two half edges. So let's see. How many faces do you see in this image? Trick question, of course. How many faces do you see in this image?
3 and 1 outer face.
Exactly. So it's 1, 2, 3, and another one outside. Everything that happens outside. So we are going to keep 3 arrays, one for the vertices, one for the faces, one for the edges. What's the only in the array of the vertices, I'll store the x, y, z coordinates of the vertex itself. The important and lengthy information of the vertex is stored only in the array of the vertices, so that's where I'll store the coordinates. I'll store it for vertex 1, 2, 3. Example is coming up in the next slide. And with each vertex, I'll store the attributes, also long information. And a vertex, as we say even here, might be adjacent to multiple edges. However, the vertex stores a pointer only to one half edge that emerges from this vertex. That is, the vertex, this vertex knows only about one of the multiple edges that emerges from it. What does a face record? It needs to know about the pointer to one of the half edges on its boundary. Every face, I'll think about it as a sequence of half edges, and the face needs to know about one of its half edges. How do I orient all these half edges? Half edge has a direction as opposed to edge that is undirectional. Half edge always have a direction, and I'll keep the agreement with you that within a face the direction of the half edges is always counterclockwise. And the meaning of counterclockwise is going to be a bit confusing. So counterclockwise means as I am walking in the counterclockwise direction around the edges, in the counterclockwise, my left hand is inside the face. My left hand is inside the face as I'm walking in this direction. Meaning that if I want to ask how the half edges are oriented towards the external edges, I think they need to be oriented just in the opposite direction. That will be a bit confusing. In normal half edges, things are a bit more natural. Here is an edge E oriented from this guy to this guy, and its twin edge, the other twin half edges, is just oriented on the second, on the other side, but oriented in the opposite direction. So, and a half edge should record a pointer to the origin, so it's know what is the vertex of the origin of the half edge, because the half edge is oriented, E itself is oriented, its origin is quite clear what it is, no confusion between the two vertices. It needs a pointer, and pointer here just means the index in the array. If you don't like pointers, you didn't play with pointers in C, just think about it as an index in the other arrays of the twin half edge. So I need to have a way to get from E to its twin half edge, the edge that is adjacent to it, and a pointer to the face that it bounds. But if I'll talk about the edge, not the half edge, but the edge itself, I don't know what of the two faces it's bounded exactly. Is this bounding this face or is this bounding this face? Half edge knows exactly to which edge it's bound. That's why we draw it a bit on the side of the edge it bounds. So each half edge is inside, quotes, one of the faces. Okay, so pointer to the face that it bounds, and it also needs to know what is the next, and you can also create a pointer to the previous half edges on the boundary of the very same face. So you know what is the next edge, maybe even the previous edge in the same boundary. So E will definitely know what is the next edge on its boundary, on its own face. Sorry. E, its half edge, it's belong to one face, so it needs to know what is the next half edge in the very same face. Maybe it also knows the previous edge. And next is, of course, in a counterclockwise, as always. Okay. Quick example. I'll just pick it's not that fascinating, and it's and there is no intellectual surprises here. Let's just check the details. You see the three arrays, one array of the faces, F1, F2, F3, F4. In this case, we didn't refer to the external face for simplicity. Here is an array of all the half edges. One is called E31, one is called E32, and so on and so forth. And here is an array of all the vertices. V1, dot, 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 all the way to V6. What do I store with every vertex? I store as accurately as I can the X, Y, maybe the Z coordinate of the vertex. Tedious information. I want to store it only once. That's the only place where I actually store the geometric information with the vertex itself. What are the X, Y, Z coordinate of each vertex? Colors, other attributes if you have any. And every vertex needs to know about only one, arbitrarily which one, of the half edges that are emerging from the vertex. So V1 needs to store a pointer to the edge E21. What is E21? It's, in this case, the only edge that leaves V1. Only half edge that leaves V1. If we look at V4, V4 is adjacent to 4 normal edges. However, it stores a pointer only to E71. That is, it stores only the index of E of V71. Where is E71? E71 is a half edge that emerges from V4 toward V6. I mean, don't try to make sense of the names of the edge. They are meaningless, just different names to every vertex. Right? So V4 needs to store right here an index of, here is I'll store an index into the array of the edges, array of the half edges, actually. Okay, now what does an edge needs to store in the array of the half edges? Let's pick one of them, E31. E31, what does it need to know? It needs to know what is its origin, where it is coming from, V2. What does it actually store about V2? Just a pointer into the array of the vertices, not the X, Y, Z coordinates. Only to store here at this part index 2 if it's the second entry in the vertices array. That's the origin of the half edge. It stores a pointer, again, an index into E32, which is what? E32 is a twin half edge. The twin half edge. So how can I know already what is, you see that I never store with the edge what is the destination endpoint. I store the origin endpoint, the origin vertex, but not the destination vertex. Why? Because I don't need to. If I want to know what is the destination of E31, what I'll ask is, what is the origin of the twin half edge? I can go to the twin half edge, which is E31, and ask what is the origin of E32, the twin of E31. You see both these edges, E31. Ask what is its origin. That must be the destination of E31 itself. So that's already how I save some information. So I store the origin of the vertex. I store the twins. I do tell you to which of what is the incident face, F1 in this case, this face, F1. And remember, for an edge, it's not clear, as I said, what is the edges that it's bounding. There are two faces. What are the faces that this edge bounds? One edge bounding two faces. Half edge belongs to one of these two faces. Each half edge knows to which of the two faces it belongs to. So E31 says I belong to face 1, and the twin half edge E32 says I belong to face F2, this face over here. What else E31 needs to know? What is the next edge in its own face? Again, the next would have been a very confusing question if it would be the full edge, because then if it belongs to two faces, each one of them, each one of the two faces go different direction, but half edge, the next one is clear. So E31, the next is E11, and E32, the twin half edge, the next is E51, going over here. So that would be our rotation. And it also knows the previous, not exactly necessary, but can help. So I can also move backward or counterclockwise or counterclockwise. And that's the whole data structure, and surprisingly it's pretty close to optimal in terms of the minimum information that I need to store. So going again after the example into what do I store? A vertex records its coordinates and a pointer to one of the half edges that are emerging from this vertex. This vertex stores only one pointer. A face needs to record only one half edge on its boundary. I don't care which one. No rules about which one of the half edges, just gives me one of them. And a half edge should record where is it coming from, not where it's going to. A pointer to the origin, to the vertex, an index in the array of the vertices, a point to know who is a twin half edge, so I can in constant time goes to the twin half edge in the same array of the edges. Tell me to which face it belongs to, this half edge, a pointer to the incident face, and the next and previous half edges on the boundary of the incident face. And that's enough. And now you can perform operations such as walk around the boundary of a face. If I start from one half edge, I know which is the next one, I know which is the next one, and I know which is the next one, so I can walk around the boundary. And I can visit all the edges incident to a vertex. That takes a bit thinking, how do I do it? How, if I start from a vertex, how do I get into all the edges? Let's go to this example back. I moved back to slide. How can I find all the edges that are emerging from V4? Let's think about it. How can I find all the edges that leaves V4? Because V4 itself only tells me that E71, one of them is the edge that is one of the edges that leaves V4. How I can find the other three half edges that leaves V4? Anybody?
If you have an edge emerging and then you do its twin, you'll go back to the edge. Or back to the vertex, and you can do next to get another emerging one.
Exactly. I can start from this edge, E71, go to the twin edge that's going back to the vertex, but I can ask the twin edge, E72, what is your next one? Right, and that will be the edge E81, and if I would keep, I'm just didn't do it in this figure, if I'll keep also the edges of the outer face, it will take me back to V4, the twin of A1, and going to the which will take me to the next, go to the next one, and so on. So in this way, you can go to both sides of each one of the edges that leaves V4, and you even get it in a clockwise or in a counterclockwise way. Right? it will be maybe easier to see if we'll think about the half edges that would have left the stars over here. You will start from one direction, going to the opposite side, going back, go to the other direction, going to the next, going back, and so on. So we can go visit all the edges incident to a vertex, and we can even answer more interesting questions like ray shooting. I have a line or part of a line, a segment, it starts at one particular point, and I want to find where are all the faces that this line or portion of the line crosses, because I can track the line, figure out that it enters one of the edges. I need maybe one starting point with one of the edges, and say, hey, line, if you enter the edge, then you must also leave the edge somewhere. Let's go over each one of the edges, half edges, that are bounding this face, asking, are you crossing this line? And one of them must cross this line. That will tell me where this line is exiting the face, and going to the twin edge. Then I know where to which other face it just enters, because the edge always knows to which face it belongs to. And following the edges again, I'll find the next intersection points. Essentially every edge I ask, do you cross this line or not? And then I can track all these phases, and furthermore, I track them in the order they appear along this line, or all this way. This will be in ray shooting application, for example, in graphics. I gave you a whole bunch of tricks of how to find if two segments crosses. What happens if I actually want to find where the intersection points? Then I cannot avoid performing division. I just need to be careful and be aware that there might be numerical error, but essentially I want to find where two segments cross each other. Not too hard to, we'll say it once in the course. If I want parametrically to specify all the points around this segment, if P1 is a vertex or is a vector or a point, think about P1, P2 is the other endpoint of the vertex, then I can look at any other point of the segment and write it as P1 vector-wise plus take P2 minus P1 times T. T is a scalar, some number between 0 and 1. So if T is 0, what do I get? Everything that happens in the parentheses times 0 plus P1. So at T equals 0, I'm at P1. When T equals 1, then what do I get? P1 plus P2 minus P1, that is, I am at P2. And if T equals half, then figure out I'm just in the middle of the segment. Right? So as T slowly increases, I'm moving along the segment slowly. And what happens if T is smaller than 0? Help. Where am I if T is smaller than 0? I'm still on the line that go through P1 and P2, but I moved either to this direction or I moved to this direction if T is larger than 1. Similarly, I can write all the points on the other segment that connects Q1 and Q2. I'll write it as Q1 plus T is already taken, so I'll use S instead of the time, as where S is 0, I'm at Q1. When S is 1, I'm at Q2. And at every time S in between, I'm somewhere on between. And now remember that P1 has two values, both the X value and the Y value. QS has two values, both for the X and the Y. And now you're asking for which value of S and T P of t equal Q of S, which is exactly the coordinates of the intersection point, gives you two equations with two unknowns, S and T, and you find it for S and T, and that gives you the intersection point. Not hard, just linear system of linear equalities with two unknowns. Anybody needs more explanation about it? What's going on? And if you've never seen it before, it might be a bit confusing using that I just suddenly jump to vector calculus without warning. You don't. Anybody wants me to go through it deeper? To okay. Let's say that not okay. So now when I have line segment intersection, just remember that the question of whether a pair of segments intersect, yes or no, I can solve robustly by playing with this orientation, because for two segments that intersect, I can ask, it must be that the two endpoints P4 and P3 are on two sides of the line through P1 and P2. So if I'm going from P1 to P2 to P3, I need to go in one direction, clockwise or counterclockwise. If I'm going from P1, P2 to P4, I must go in the opposite direction. And analogously, I need to check also for the opposite direction. I need both conditions to hold, because otherwise I can run into conditions like that this segment will think the line through this segment divides the two endpoints of this segment, but not the other way around. And as usual, all the extreme cases needs a bit extra attention, like two segments that cross just at an endpoint, one endpoint of a segment that is exactly on the other segment, two segments that are both collinear and one starts where the other one ends, and so on, all these cases. And when I'm going to describe the line sweep algorithm, which I'm going to describe now, let's assume that none of these cases happens, because making general position assumption. General position, I just introduced a tiny bit of noise into the whole system. So these two segments with this a bit noise, either they start crossing or they stopped crossing, but if they cross, they properly cross. Properly cross like this. Okay, and similar for the other cases. And I don't know if we'll talk about it. The textbook contains a description of how to do the line sweep algorithm when you are paying attention to all these assumptions as well, catching all these cases as well. At the moment, I'll assume that if two segments are either disjoint or they properly cross each other from side to side. And I want to talk about the plane sweep algorithm. Why do I need the plane sweep algorithm? It's kind of a paradigm more than algorithm, because there is many algorithms, in plural algorithms, that starts using the same idea of the plane sweep algorithm. And I'll just suggest one application here, or two applications. One application will be, I have a set of segments. For example, I had a VLSI design and designed a board, a printed board, and if I did it properly, then none of the segments in my printed board are no two segments of my printed board should cross if everything is okay. And all I want to ask is either any pair that cross. And all I need is a yes/no answer. If my drawing is correct, then I don't have any answer. And as we'll see, in the other application will be find all the intersection points or all the pairs that cross each other. That is, tell me exactly where are all the intersection points that cross each other. Okay, which would be a generalization of the very same question. And let's see how it is done. And the big picture that you want to keep in mind is that you have your set of segments, segment 1, segment 2, segment 0, and segment 3. And I want to ask either any pairs that intersect or not. And what I'm going to do is to sweep the plane with a line. And in some textbook will say this is a line sweep algorithm, while other textbooks will say no, it's a plane sweep algorithm because you are sweeping the plane. So and they'll say if you are sometimes you're sweeping with a plane the 3D world, but the plane sweep algorithm refers to the two-dimensional world, etc. So just remember that the term plane sweep might sometimes refer to sweeping the plane with a line, and sometimes it will refer to you're sweeping the space with a plane. Anyhow, we are talking about the two-dimensional plane, so I'm going to sweep to move a line that will move all the way from left to right, and this line slowly moves among the segments, and every moment in time, this line needs to know about the status. We will use this term status, and the status is who are the segments that are stored that are crossed by the line at this moment. Once again, the status stores the segments that are currently crossed by the sweeping line. So the status right now is all the segments: segment 3, segment 1, segment 0, segment 2. And furthermore, it will even store them in the correct order. Who is below whom? The status will say, oh, I cross S3 before I cross S1 before. But at other points, right here, the status will say, oh, only segment 1 is in the status. That's why it's blue. Being in blue in this app is that you're in the status. And when we start the line sweep, none of the segments are in the status. There are no intersection at all. The line sweep doesn't store any intersection. And the line sweep is just a mental creature that we are imagining that is running there, and it's not one of the segments. Again, the line sweep is not one of the segments. It's a vertical line that moves all the way from minus infinity to plus infinity, and along the way it checks some things for us. In particular, it will check for us for the segments which are in the status. For the segments which are in the status, the line sweep intersect, it will ask, are you intersect between yourself? Hey, two segments like S1 and S0, are you guys crossing each other at any time in the future? And they'll say, no, we don't. Status, and the line sweep will say, okay, let's move on. And as the line sweep moves, at some point it will start crossing S3, segment 3. And then it will ask S3, hey, do you cross any of the segments that you are in the status right now? In this example, no, it doesn't, but if I move it, of course, it might. And so on. And the save up, we are storing some time because when the line sweep asks S3, are you crossing any of the other segments? It will actually ask, hey S3, are you storing the nearest segment to you? The nearest along the segment. So S3, who is the nearest segment to you? It happens to be S1. Hey S3 and S1, are you crossing? And not in this example, but we will see that it's enough just to ask for a segment. Are you crossing the one just immediately below you or just immediately above you? It will be somehow sufficient for the task to check if any segments intersect. So we can do this process slowly by moving this line sweep continuously and letting this thing change until we'll realize that if the line sweep moves and doesn't start crossing a new segment or doesn't stop crossing a new segment, that nothing has changed. The status doesn't need to know about any changes as long as it didn't start hitting a new segment or it didn't stop intersecting a new segment. Like right now, it intersects S1, and if I'm moving it a bit further, it stops intersecting S1. So that will be an event. Every time that the line sweep start or stop crossing one of these events, something change. And between events, nothing change. So what I'll do is, instead of doing this continuous, elegant move, gradual smooth move, I'll prepare ahead of time an event queue that tells me what are all the X coordinates, that something interesting happens. And after I'll do it, I will move the line sweep only via a sequence of jumps, only from one event to the next event, to the next event, to the next event, and only in the event something change. And I will feel no need to worry about, here is one event that happens because segment 2 ends. Here is the next event that happens because S3 ends. And between these two events, nothing interesting happens. So the algorithm will not waste any time right here. It will just jump to the, it will just jump from, okay, it will just jump from one event to the next event, to the next event, and so on. And that's why. So what are we trying to gain? Let's say for the question of either any pairs that intersect, just to tell you where are, what is realistic to hope for. I can check for each pair, do they cross or not, which will take n square time, theta of n square time. Check each pair, do they cross or don't cross. If n is huge, a lot of it is coming from geographic applications. I want to merge maps. Maps are a big things. N square is way too much. So what do I hope for? To answer this question of do any segments intersect, but why the n square? Because I check that's the number of pairs of segments. Instead, I want to answer this question in order of n log n, to answer either any pairs that intersect. Now, what happens if I do want to know what are all the intersection points? Then I would like to have n plus k log n. What is k right here? N is a number of segments. What is k? Well, if possibly I have n square intersection, possibly almost every segment intersect almost every other segments, like in this case, well, n half horizontal, n half vertical. Possibly the number is much larger, so I cannot really hope for n log n if I want to find all the intersection points, but possibly none intersect. So in this case, I will run in n plus k. K is a number of intersection points times log n. If there are a lot of intersection points, it will take a lot of time. If there are none, no intersection, it will still take only log n. Okay, so that's where we are going to continue next class. Exactly of describing what are the elements of the line sweep. And somewhere during the elements of the line sweep, we will also use to know, hey, a query point, are you above or below a segment, which will use the exercise that we started with. Questions? Okay, thanks everybody.